Hello everyone, my name is David Jamieson, and on behalf of the School of Physics at the University of Melbourne, I'd like to welcome you to our fifth and final July lecture for 2020 on the theme of physics and life. First, I'd like to acknowledge the Wurundjeri people, who are the traditional custodians of the land on which the University of Melbourne is built, and I'd like to pay my respects to their elders, past, present and emerging. So our fifth lecture for tonight is by Katie Auchetll, who speaks to us from summer in Copenhagen. Katie has a PhD in physics and astronomy from Monash University from 2015, and during her study she was also a Smithsonian Astrophysical Observatory pre-doctoral fellow at the Harvard Smithsonian Center for Astrophysics in Boston. She went on to join the Center for Cosmology and Astroparticle Physics as a postdoctoral fellow at the Ohio State University in Columbus, Ohio. And then in 2018 moved to the Niels Bohr Institute, which is part of the University of Copenhagen, as an assistant professor, where she both teaches and does research. Then in early 2020, she joined us in the School of Physics. When I say joined, subject to the restrictions of travel at the moment, but she joined us in the School of Physics as a senior lecturer and a fellow in the Australian Research Council Centre of Excellence for All-Sky Astrophysics in 3 Dimensions. And at the same time, she also holds an adjunct professor position at the University of California, Santa Cruz. Now, just breaking news, in 2020, she was awarded the prestigious Louise Webster Prize, which is awarded annually by the Astronomical Society of Australia in recognition of her outstanding research by a scientist in their early postdoctoral career. So congratulations for that, Katie. Her research interests involve studying the extreme death of stars and makes extensive use of astronomical observatories in space. So Katie, please tell us all about the elements of life from supernovae to planets.
Awesome. No, thank you so much, David, for this great introduction. Thank you so much for allowing me to be able to talk to you today about something that I find very dear to my heart, understanding the elements of life from stellar death and how that kind of connects towards the planets and understanding where we come from and what we're made of in the universe and the different elements associated with this. And I'm very lucky to be able to give this talk today, as this is actually the last talk in this series for this year. But also, luckily, I'm very honored to give the last talk for David's. David has been running these July lectures for the last 3 decades. And I feel very honored that I can actually be able to give his last talk talking about these elements of life. So thank you, David, for running an amazing series over the last few years, or last decades or so. Okay, so as I said, I'm going to talk about the elements of life and how they connect to supernova, or the death of stars, and to planets for this. But before getting into this, let's step back a bit and start from the very beginning. So to build a planet like the Earth we live on, you need a lot of material. In particular, you need a lot of heavy elements, like the iron we find in our blood, the oxygen we are all breathing, the silicon that is the fundamental components in the processing chips that are found in your computers that allow us to connect to each other today. However, when we look out into the universe and measure the different elements that make up what we observe, what we find is that the visible universe, so what we see by our eye, is mostly made up of 2 elements, hydrogen and helium. And these were created within the first 2 minutes of the Big Bang, or within the first 2 minutes of the beginning of the universe, nearly 13.8 billion of years ago. Together, hydrogen and helium make up nearly 99.9% of known matter in the universe. However, we know that our planet and you and I are made up of elements much heavier than hydrogen or helium, though. And so in fact, we find that there is a whole range of elements or metals, in which astronomers refer to any element heavier than hydrogen or helium, in our universe. And in fact, chemistry, a field of study in science, has for many years been studying these elements on Earth to try to understand the properties and fundamental constituents of these elements and group them together based on their similar chemical behaviors and their properties, as we show here in what we call a periodic table of elements. However, if most of the universe is made up of hydrogen and helium, then all these other elements that we find in our periodic table must have come from somewhere if they weren't man-made. And the key to understanding the origin of the elements in the periodic table, and that what we see in our universe, is by studying the life and the death of stars. But first, we should start from the beginning of a star's life. So stars begin their life as vast clouds of cold molecular hydrogen and helium, like those shown here in the Eagle Nebula. And these objects correspond, or these big vast clouds of material, are the building blocks of a new generation of stars. However, these clouds of gas will usually happily remain in these beautiful forms that we see here in the Eagle Nebula, as long as the energy of the hydrogen and helium atoms is sufficient enough to fight against the continual force of gravity that always aims to try to push them together for this. However, if the energy or pressure of the hydrogen and helium gas is not strong enough to fight against the force of gravity, this cloud of hydrogen and helium will actually begin to collapse, birthing the next generation of stars. And so in this image here, we have one of the largest, most prolific star-forming regions in our sky. And this is found in one of the Milky Ways, so our own galaxies, nearby galaxies, called the Large Magellanic Cloud. And these beautiful blue diamonds that we see in this image are actually very, very massive stars, up to 80 times larger than our own sun in terms of its mass. And these were all formed from the molecular cloud, or that hosts it at the moment, that had collapsed into these beautiful objects a number of years ago. However, the lifetime of stars we find in these beautiful stellar nurseries are actually dependent on the amount of fuel available, or the amount of hydrogen or helium available to the star to be able to devour. And also related to the rate at which the star is actually able to devour this material, though. Or another way to kind of think about this is that the lifetime of the star depends on the mass of the star, so how heavy it is, divided by the luminosity, or how bright the star happens to be. And so from looking at a large number of stars in the universe, we as astronomers have actually gone out and measured the mass and luminosity for a large number of stars. And this is what you find here, where we have plotted on the horizontal axis the mass of a star, and on the vertical axis we have plotted how bright they are in terms of units of the sun. And so what we find is that for most stars in our universe, how bright a star is proportional to how massive they are, to a power of 3.5. And so this means that we can take this relationship, since we're able to observationally constrain it, and replace the luminosity part of our equation that we show here. And what we get is that the lifetime of a star that we observe in these stellar nurseries is dependent on the mass divided by the mass to the power of 3.5. But we can actually simplify this and say that actually the mass of the star is inversely proportional to the mass to the power of 2.5. But what exactly does this equation mean? Well, particularly, this implies that the more massive a star is, the shorter the lifetime of a star will be. And so this fact actually has important consequences for understanding where the elements of life and those heavier than hydrogen and helium come from, since the type of element that a star can produce depends heavily on the mass of the star itself. But then how do you produce elements heavier than hydrogen in a star then? Well, this process is called nuclear fusion. And so nuclear fusion is the process in which the nuclei of two atoms come together to create a new atom or element. Nuclear fusion is the lifeblood of a star, and the enormous luminous energy of a star comes from this nuclear fusion process that occurs in the center of the star itself. And in fact, this is the reason why our very own sun shines. It is currently converting hydrogen into helium into heavier, hydrogen and helium into heavier elements, following these chains that are shown in the image here, using nuclear fusion, and the light that we see from the sun is the energy released from this process. However, as I said previously, which elements that are produced within the belly of a star depend highly on the mass of the star itself. And so for all stars, they all begin fusing hydrogen into helium when they are born. And so this phase of converting hydrogen into helium occurs for most of the life of the star. And so most stars that you see when you look out into the night sky are actually completing this process. However, when all hydrogen is used up within the belly of the star, there is a moment when the output energy created by the conversion of hydrogen into helium is now not enough to fight against the constant inward pressure of gravity. And so what will happen is that gravity will actually compress the star and heat up the insides of the star completely, causing the pressure and temperature inside the star to increase dramatically until it's suddenly so much that the temperature and the pressure is high enough that it kickstarts the next phase of its life. And the next phase of the life of a star is when a star will begin fusing helium into carbon and oxygen. However, at this point, this is when the mass of the star plays a very important role with what happens to the star next. And so for stars lighter than about 8 times that of our own sun, though, in terms of mass, they're not large enough to be able to produce heavier elements than carbon and oxygen. And so what will happen is that fusion will actually stop in these stars when all the helium is used up in the belly of these stars. And what will happen after this, the next phase of their life, will correspond to that the carbon and oxygen core that was left over at the end of that part of its phase will be left over, and any of the material in the outer layers of the star that had not been converted into heavier elements yet will then be expelled into the environment in these beautiful objects called planetary nebula. However, even though these are incredibly beautiful, from the perspective of the light element life, you might have noticed that these stars, even though they produce the oxygen we breathe, or the carbon that makes up the fuel or batteries which power your cars, these elements are actually locked up in this carbon-oxygen core that are found at the heart of these beautiful nebulas. So then how do these elements then end up, either in the planets or on Earth, for us to be able to use then? Well, one of the answers lies in the most massive stars, where here we say the most massive stars are those at least 8 times the mass of our own sun. So unlike the stars that have similar mass to our sun, which are not heavy enough to be able to begin carbon to oxygen fusion, these objects are large enough that they can actually begin forming heavy elements all the way up to iron. However, again, you might have noticed that all these elements are locked up inside the belly of the star. So then how does the iron or silicon or oxygen that is found within the center of the star here make its way into our bodies, or the air we breathe, or the computers we're using right now? Well, the key to this is the formation of the iron core at the center of this massive star. And so the formation of this iron core actually marks the beginning of the end of the star's life. And so when the iron core becomes heavier than about 1.5 times in the mass of the own sun, the core is just way too heavy to be able to support its own weight against gravity, and as such, the core will actually begin to collapse on itself. And so when that happens, the outer layers of this star will initially begin to collapse along with the iron core, but what will happen is that they will rebound with enormous release of energy and are thrown out violently outward into the environment or into our universe, and what we see as a supernova explosion, as shown here in this very beautiful video. And so one of the most famous examples of one of these core collapse supernova explosions was actually one that occurred right in our nearby neighborhood. And so this supernova is Supernova 1987A. And it is called this because it occurred in 1987, and it was the first supernova detected that year, and so hence it was called A. Astronomers are not necessarily unique in the way that they name things. And so this supernova occurred in the Milky Way's nearby galaxy called the Large Magellanic Cloud. And so living in the Southern Hemisphere, we were actually very lucky because we can actually come across some of the dark enough skies that we can actually see this galaxy by eye. And in fact, when this massive star went supernova on February the 23rd, 1987, the luminosity of this explosion was bright enough that it outshone the host galaxy itself, and it was even visible by eye for many months after its explosion. And so we have actually been incredibly lucky that this supernova occurred so closely to us, because we have been able to observe this object for nearly 3 decades now and watch and study the evolution and properties of a supernova in real time. So as you can see here, we have a series of snapshots of the expanding ejecta that comes from the supernova explosion as it expands into the environment. And so this is all the stellar debris and the material that was produced within the explosion, and also the swept up environment, producing these beautiful images that we see in X-rays from this. And at the bottom here, you can actually see the snapshots in a video expanding out as it evolves. However, even though we were very lucky that this happened to go off nearby, usually we are not that lucky, in that supernova explosions, or the death of stars, usually do not occur this close to us, or they're not necessarily easily visible by naked eye like this historic event was. So then the question is, then how do we detect the stars that are in their final stages of life if they happen not always to occur so close to us? Well, the way that we detect these violent ends to the life of a star is that we usually use a wide variety of optical telescopes, similar to kind of what your own camera, but that have very large lenses that are located on telescopes located across the whole world, which monitor the sky every night, looking for these extreme luminous bursts of our light that indicate that a star may have died. And so as a supernova are among the most energetic events in the universe, we can easily detect stars dying in galaxies much further away from us than we can see by eye. And due to the fact that we also now have the ability to be able to do these observations robotically, we have also been able to detect many of these supernovae per night. So for example, one survey that I'm a part of is called the All Sky Automated Survey for Supernova, or ASSASSIN. And this has detected over 1,000 supernova, or death of stars, since 2013. And so you can see we've been able to detect a huge number of these objects across the whole sky from this. However, even though we're able to detect many of these sources quite easily now, and detect them in galaxies very far away from us, this actually can be quite a bit of a disadvantage in some way, especially if you want to try to understand the type of elements that a star produces and how they end up into the environment, that either end up into the air we breathe, or in the soil of our Earth, or in the components of the computers we are now using to connect with each other. And so the reason why this is a disadvantage is that these supernovae we detect in these surveys are pinpoints of light that are not very well resolved. And so, for example, here are a few images of supernova that we detected using a telescope in Hawaii over the last year or so. And so what you can see is that these pinpoints of lights in the galaxies far away. And so it's actually quite difficult to see the immediate surroundings of the star that is exploding. And also it can be difficult to see the actual type of elements that are produced in the explosion, or even how they are actually thrown out into their environment. And so ideally, what you would want is you would want a supernova to occur much more closely to us, something similar to supernova 1987A. However, as I said, supernova, or the death of stars nearby, don't actually occur very often. In fact, they are actually quite rare. However, on average, we're expected to see about 2 to 3 supernova per century per galaxy. But even in our own Milky Way, or nearby galaxies, we find that we see much less than this. In fact, in our own Milky Way, we've only detected 8 supernova, or the death of stars, in 2,000 years, which is much less than the 2 to 3 per century per galaxy than what we expect. And so as a consequence, this actually makes it difficult to study many aspects of the explosion directly. However, astronomers have a way to be able to get around this, and this actually constitutes some of the research that I actually pursue. And so the way that we get around this is by using something called a supernova remnant, which are the remains of stars that died thousands and hundreds of thousands of years ago. And so the advantage of these beautiful objects that I show here on the screen is that compared to supernova that we detect in our nightly optical surveys of the sky, which are only bright for very short periods of time and located very far away, these beautiful objects are located quite close to us, and they're observable in multiple wavelengths for thousands of years. And so in our Milky Way and nearby galaxies, the Large and Small Magellanic Cloud, there are over 300 of these objects located close to us that allow us to directly study and probe the type of elements that are produced in the belly of the star and how they are thrown out into the environment, enriching our galaxy in metals. So how do we be able to take these beautiful objects, and how are we able to actually do this, though? But before we go into how we actually try to pinpoint the different elements that are found in these stars, right, the first question you probably are wondering, well then how do we determine which of these beautiful objects actually came from the collapse of a massive star if the star died thousands of years ago and we were not lucky enough to see it at that point? Well, the easiest way to determine whether these beautiful objects arise from a core collapse of a massive star dying is through the detection of something called a neutron star. And so a neutron star is a very dense core that can be left over after the explosion of a supernova. These objects usually only are produced by collapse of a massive star, and they usually are born very rapidly rotating, as you can see here in this image. And so what that means is that because they're rapidly rotating, they can easily produce a lot of their own luminous multi-wavelength emission, which makes them easy to spot at the heart of supernova remnants, or the leftover of stars. And so here is one famous example of a neutron star called the Crab Nebula. And so now that we know that the neutron star is kind of the smoking gun signal for the discovery of a core collapse supernova remnant, we can go back to our sample and select the ones that happen to have this bright neutron star at the center of our galaxy, or at the center of our supernova remnant, though. And so if we actually happen to see this neutron star at the heart of it, we are very confident that this object that we observe arises from a massive star undergoing core collapse. However, unfortunately, only a third of that we see show bright observable neutron stars that look like what we see in these images. And so as a consequence, we need another method to try to work out whether these supernova remnants actually come from the core collapse of a massive star or not. Well, another way we can do this is actually look at the stars directly around a supernova remnant, or the leftover of a star exploding. And what we can actually do is use the ages and masses of those stars in the immediate vicinity around these supernova remnants as to be able to understand what type of star went off. The reason why is that these stars around the supernova are likely representative of the mass and ages of the star that actually exploded, producing this beautiful object we observe, though. And this is because massive stars, when they are born, tend to not travel very far away from their birth sites. And so they actually kind of stay with the same stars that they were actually born with from that. And so let's take the example here again for supernova 1987A. And so what we have done is actually taken all the ages and the masses of the stars around this supernova and determined what type of stars were actually in the vicinity of this supernova remnant. And so what we find is that most of the stars, should I say, that are surrounding supernova 1987A have masses around approximately 15 solar masses, as you can see here in this spike of this image of this graph that we have in the below. And so what this implies is that this remnant likely arose from a star with approximately 15 solar masses, or 15 times that of our sun, that underwent core collapse. And this has actually been confirmed by multiple independent measurements. And in fact, we can go do this same technique to many supernova remnants in our nearby galaxies. And so here is a beautiful radio image of the small magnetic cloud, which is, which again, you can actually see this by eye, this galaxy by eye, if the sky is dark enough. And so the Scion circles that we can see on this image corresponds to the positions of the supernova remnants, or the remains of the exploding stars. And so doing the same trick that we did before, where we looked at the masses of the stars around each supernova remnant, we can then see, for example, this supernova remnant here likely arose from a star that was about 8 to 12 times that of our sun, because most of the stars seem to have this mass. Or we can look here and see that this star, for example, most likely arose from a star that was 21 times or more larger than our sun, from this. And so all these can be kind of independently confirmed. However, this type of study where you can actually resolve or look at the stars around the remains of a supernova explosion are only good for, this technique is only good for for remnants that are found in nearby galaxies, like the large and small magnetic cloud, though, because we can actually see the stellar populations quite clearly. However, we can't always use this method, especially in our own Milky Way. And so as such, it can actually be difficult to quantify because it's difficult to quantify the properties of the stellar populations in the, around the supernova remnants in the Milky Way. And so then we have to do another method associated with it. And so what we can actually do is take advantage of the shapes of these beautiful objects, though, because the shapes of these objects can actually give you a hint to the origin of their explosion. And so even you as the public can actually do this yourself by eye. And so remember how I said that stars are born from large clouds of hydrogen and helium. Well, most massive stars tend to be born in the densest of these clouds. And the density of these clouds naturally shapes the explosive origins of these remains. And so what we find is that the structures that arise from the massive star dying tend to be more asymmetric in shape or more elliptical in shape. So they're not very spherical or in the way, or symmetric in the way that they evolve into the environment, though. And so if you see a shape that one of these objects that turns out to be kind of a little bit weird in the way that it looks, it's likely that comes from a core collapse of a massive star. And so here I've plotted some examples of these objects where you can see that their symmetry, that they're very kind of asymmetric or even elliptical in the way that they have expanded out into the environment. And so with this knowledge in hand, that to constrain the core collapse of a massive star is that you can use a new discovery of a neutron star. You can look at the stellar populations and look around the star and see if they have the similar mass, and also look at the shapes of these. We can take this knowledge in hand, and we can take our beautiful sample of supernova remnants that I showed before, though, and select the sample that arises from a core collapse of a massive star. And so once we have our sample, we need to now understand how we detect the elements that are produced by a star and in the explosions of these sources. And so let's go back to this video here. So as I said, when a star dies, what happens is that an enormous amount of energy from this explosion is converted into kinetic energy. And so kinetic energy is a form of energy that an object gains when you accelerate something. And so what happens is that this kinetic energy is so fast that it forms an expanding shock wave of stellar debris that plows into the environment, as you can see here. And so this shock wave is similar to what when you have a still body of water and you drop a pebble into the water. And what you notice is that expanding rings kind of expand away from the entry point of the pebble into the water. And so this is no different to what happens in a supernova explosion, but of course in a supernova explosion, it occurs on much larger and extreme time scales. And so when this shock wave moves out into the environment, what happens is that it will collect material in addition to the stellar debris from the now exploded star. And that will actually cause the shock wave to kind of start to slow down as it collects more and more material. And so when it slows down, the freely expanding stellar debris of this now destroyed star will then crash into this shock wave, causing it to be heated up to millions and millions of degrees, making these elements that we produce in the belly of the star, but that are now expanding out into the environment, bright in X-ray wavelengths. So the same wavelengths that you use if you happen to go to the ER and have to have a scan of your bones if you've broken a bone. And so a lot of these beautiful images that you see here actually are the elements of life glowing in these X-ray wavelengths. However, unfortunately, or maybe actually fortunately for us, we can't use instrumentation on Earth to be able to study the stellar debris of that these supernova or these elements glow in. And the reason why is that X-rays are very powerful, and in too high of a dose, they're actually detrimental to us on Earth. However, Earth is wonderful and has a natural defense system for us to be able to protect against these harsh wavelengths. And this being our atmosphere, which actually absorbs these high energy photons before they can actually reach us. So what that means is that for us to be able to study these beautiful objects, we have to go out of the atmosphere and go into space. And so here are some of the telescopes that are in space at the moment that correspond to approximately the wavelength that they observe in. All the instruments we are used here are used for a wide variety of different studying a wide variety of different astrophysical phenomena. And so for studying supernova remnants and the elements of life produced in these explosions, what we do and use is predominantly these ones here. These are the Chandra X-ray Observatory, the XMM Newton Observatory, and the NuSTAR or Nuclear Spectroscopic Telescope Array. The reason why we use these is that these perfectly observe in the X-ray wavelengths in which we expect to observe a large number of the elements produced in a supernova explosion. And so when we're actually lucky enough to get time on one of these telescopes, which for me is still one of my most amazing aspects of my job, that I can actually have a telescope in space point at something that I think is very interesting. What we can actually see from one of these observations using these instruments actually looks like this. And so this is what we call an X-ray spectrum. And what it measures is essentially the brightness of the source, which is shown on the vertical axis, as a function of the energy of the source in X-ray wavelengths, which is shown on the horizontal axis. And so this is an X-ray spectrum of the core collapse supernova remnant called Cassiopeia A, which is shown in the top corner here. And so this spectrum is quite magical to me, though, because this spectrum has imprinted on it all the elements of life. In particular, these bumps you see in this spectrum that we observe actually correspond to different elements. So here, for example, is the iron, similar to the iron that is found in your blood or makes the soil of the outback of Australia red. And so I'm also plotting, in addition to highlighting which element, where this element is, you'll see in the top inset that you can actually see the distribution of the iron in this supernova remnant, though, as it expands out into the environment. And so here we actually have calcium, the very element that makes up your bones, as strong as steel. And then here is argon, the inert gas that is found in fluorescent lights and used in a wide variety of industry applications due to its non-reactive nature. Here is sulfur, which is a vital element for all forms of life, as it's one of the components of 2 amino acids that are the structural units that make up the proteins in our body. And then here is silicon that makes up a number of our computer and electronic components. While here is magnesium, which is widely used in construction and medicine, and is actually one of the elements that are actually essential to all cellular life. While here, this deceivingly small little bump is actually oxygen, the same oxygen that makes up the air we breathe and forms the fundamental components of water that we drink of or that we found in our ocean. And so one can see that one of these objects produces a whole wide range of elements for this. And in fact, if you look at many of these objects, you can actually estimate the amount of each element that is produced in the core collapse explosion of a massive star in units of the mass of our own sun. So what we find is that these type of events produce lots of carbon, magnesium, silicon, and iron, and large amounts of other elements that are crucial for life here on Earth. But one of the most striking features of this plot, or all of these supernovae, is the fact that each time a star more massive than our own sun violently ends its life in a supernova explosion, it produces at least 1 sun worth of oxygen in terms of mass. But as we know the amounts of elements produced in these now we know what the amounts of elements and the types of elements that are now produced in these explosions. The next question that you might have, well, how do these massive stars throw out their elements and distribute them into the environments for us to in the end be able to take advantage of them? So previously, I had said that supernovae are usually just way too far away to be able to properly determine how they are thrown out into their elements are thrown out into the environment. And so this means to try to understand this, we have to go to simulations to work out how do we expect these supernovae to distribute these elements when they explode. And so luckily, we're now at a great point of time in terms of studying supernova and how they distribute their elements into the environment, because 3D simulations of these violent ends to these massive stars is now getting to the point that they are starting to make predictions of observables that we as astronomers can actually test. So here is this simulation, right, which predicts that, which encodes theory that predicts that each element should be ejected differently. And this should be related to how they're produced within the star. And so what you can see in this simulation is that different colors correspond to different temperatures. Or another way to kind of think about it is different colors correspond to different elements. And these elements, as you can see, have different distributions within the explosion and how they are passed into the environment in different ways. And so let's go back to Cassiopeia A here, the supernova remnant we were looking at the X-ray spectrum of before together. And so where we were able to see all the different elements of life produced in this explosion. So in addition to when I was showing the X-ray spectrum, we also saw that the distribution of elements in the inset as they were being thrown out into the environment. But let's put them all on one page together so that we can see what all the distribution of the elements are. Though where we have the lighter elements, though, are the ones on top. And by eye, visually, they look a little bit more evenly distributed into the environment. While the heavier elements at the bottom, especially the iron, looks like they are thrown out into the environment a little bit more randomly or more asymmetrically in the way that they're distributed. And so even though I had quantified this by eye, though, because our eye is actually very good at picking up different structures, though, we can actually go out and measure this and make this more kind of scientifically robust, this prediction. And so we can actually measure how symmetric or asymmetric the distribution of the elements that have been thrown out in different supernova explosions, and determine whether this they expand into the environment, and whether that is uniformly or a little bit more randomly in the way that they're distributed. And so what we have plotted here is how symmetric or asymmetric the elements that we saw in Cas A are, and how they're distributed in their environment in the remnant. And so it seems that what we could predict by eye, that iron distributed in Cas A seemed to be more asymmetric in the way that it was thrown into the environment, is actually true. And it's more asymmetric compared to the other elements we see at the bottom here for this. And so it seems that consistently the light elements we observe in the death of massive stars are like this, like oxygen, for example, is more uniformly distributed into the galaxies during these explosions, while the heavier elements tend to be more randomly distributed or more asymmetrically distributed into the environment. And so what we find is how they actually are distributed actually depends on where these elements are produced in the star and in the explosion, though. And so what we find is that metals created closest to the center of the star, or center to the iron core, right? They actually tell us about the inherent properties of the explosion of the massive star, and also what was happening inside the belly of the star. And so this was previously quite difficult to be able to do, because remember I said the stars are pinpoints, supernova explosions are pinpoints of lights that we see very far away. But being able to look at these structures that are extended across the sky, we can actually work out things that are actually hidden from view from us in these objects. And so now that we know that the collapse of a massive star produces a wide range of elements, and we can actually study how these elements throw these distribution into the environment, the next question you might have is, well, what evidence do we have that supernova explosions of massive stars contribute to the elements we detect on Earth? Well, the evidence that we have actually comes from the measurements of iron, in particular a type of iron isotope, where an isotope is just a different version of iron or an element that we usually think of when we're looking at our periodic table of elements, but it has slightly different properties. And so in particular, here we're measuring an iron isotope called iron 60. And so this type of iron isotope is produced in supernova explosions and massive stars. And what has been found is that when one measures this amount of this element, though, in samples of the Earth taken in the deepest parts of the ocean, or from the crust of the Earth, or even from the rock samples from the moon, we find the amount of this iron 60 is significantly enhanced relative to the amount of normal iron, or normal iron that we usually think of and that we measure on Earth. And so when you can see here, this is essentially the measurement that people have been able to take, though. And so the only way to try to explain this enhancement of iron is that there must have been at least one core collapse supernova explosion of a massive star that went off close enough nearby to us, though, where nearby here corresponds to about 100 parsecs away, or in kilometers is 3.1 times 10 to the 15 kilometers away from us. So we're lucky we're still safe from these. And this massive star that went off nearby must have died nearly 2 to 3 million years ago, or we would not be able to explain the bump that we observe in the measurement of this iron 60 component that we observe. And this is some of the strongest evidence that suggests that the elements we observe come from supernova explosions of massive stars. And so the next time when you look at our planet and admire like the color of the Australian desert, or go swimming in the ocean, or even take a breath, you can be thankful, though, because even though these stars that are now long gone and these beautiful objects we observe and think, without these objects, we actually would not be here today, because these objects, even in their final endpoints of their life, provide us with the next part of our life and provide us with the elements of our life for this. And so thank you so much.
Well, Katie, thank you very much for that amazing and very colourful lecture. We have a number of questions from the Q&A. I should have mentioned at the beginning, if you're interested in asking a question, please use the Q&A button that you should see on the bottom of your screen. So let's start with one from Ashish Singh. Do you think that there exist conditions for the basic forms of life to begin in the regions around the supernovae?
Yes, so we actually do detect elements that are associated with life around supernovae, so not in X-rays, but in other wavelengths. And so we find complex molecules near these objects that correspond to the element or different elements or different atoms or components that we require. However, supernova explosions, as I said, are some of the most energetic properties in the universe, which actually makes it very difficult to be able to live there because it's a very extreme environment, which probably doesn't make it as safe for life to be able there. So we are lucky enough because we have the atmosphere and the Earth being able to kind of protect us and shield us from the extreme nature of space. And so while there is while we do see evidence of element that may suggest life, it probably is not the most nice place to be living from that. Okay.
Another question here about the models that you used from Sai Pemaraju. The stellar masses from the neighbouring stars that you used to deduce the mass of the star that exploded. Is this a very high precision model, or is it only a rough approximation? How accurately can you depend on that method?
Yeah, okay, so it's not a model, so it's not necessarily a model that we're observing. What we're actually doing is measuring the actual observed properties of these stars. Mm-hmm. Though, of course, it does depend on some underlying physics, we assume. So for each of the stars, they're pretty accurate in being able to measure it. But associating with the supernova remnant, we can only say it's either small, medium, or large is the best way, I would say, from doing those looking at the stellar properties around the object. So you can't say that it was exactly a 15 solar mass star. You have to use a lot of other indirect evidence from actually calculating, for example, the different elements and how much they are and comparing it to models. So you can rule out that it's not a small one, right? You can say it's likely a big one, but of course, the best way to do this is actually, if you see a star and you've measured it properly, and then you see it go supernova like supernova 1987A, we knew what the star properties were, we knew what it was, and so we definitely can associate it with this. But of course, these objects are thousands of years old, so we miss that a lot of things, although some ancient civilizations actually did detect some of these, which was kind of exciting.
Yes, okay, so a question here from Thomas Berendt. What does the lack of the observed supernovae in the Milky Way galaxy say about the timeline of the galaxy evolution, if anything, or is it just a coincidence?
So the lack of supernova in our own Milky Way is actually probably dependent to the fact that the Milky Way is incredibly dusty, and that it may be hidden through many layers or huge amount of dust that is hiding the supernova from this. And so, we should have seen one in our Milky Way. But it's likely that because of how we're positioned in our universe or in our Milky Way, that maybe they could have happened on the other side of the sun. And it's just that we have too much extinction or dust in the way to be able to detect this. So And so I don't think it has, I think it's just mostly an observational effect than anything kind of more fundamental from this. But of course, that is a question that we're trying to work out whether it's true. And it would be amazing if we can actually detect a supernova go off in our Milky Way. And to be able to do this, but to kind of compensate for the huge amount of dust, which makes it more difficult to see them in optical wavelengths, we can now use neutrinos to try to detect this. And so that's actually what was done for 1987A. And so now we have very nice instruments that can actually do this, that are searching and hoping to see the next star go off in our universe, in our Milky Way.
I have to say, given that we're facing this very dangerous pandemic, would it be dangerous if a supernova went off in a nearby star? Or how far away to be safe do we want to see the next supernova? Not the nearest star, presumably.
So, you know, we don't have to worry about our sun, right? Because our sun will go off quietly, right? And we've got plenty of time from this. So we won't have to worry about this. But it would have to be relatively close for us, where I said within probably 100 parsecs, which is 3.1 times 10 to the 15 kilometers away, would be probably a little bit of a worry from this. But most of them occur much further away from that. So even if a star does go off, we shouldn't worry about it. We should just be able to admire how beautiful it is and be able to see a new star born, essentially this bright source in the sky, which you can sometimes, if it's bright enough, can actually see during the day.
Oh, that'd be a wonderful thing.
Yes, no, I really hope for it.
A question now from Charlie Sherney. Our sun is a third generation or second generation star. How does such a new star form after the supernova and still depend on the essential hydrogen and helium fuel?
Well, so the universe is still actually, so even though a star, you know, you produce a star, though, from hydrogen and helium, it doesn't completely remove all the hydrogen and helium. There are still huge amounts of this in our universe. And so even though it throws off, right, you'll distribute the elements into the environment, right? This enriches these hydrogen and helium clouds, but the shock waves from, or the energy from the explosion can actually trigger a new star being born nearby, though, in a region of the cloud that actually had hydrogen and helium. And so it can it's this kind of ebb and flow. And of course, you don't always, the star doesn't always convert 100% of its hydrogen and helium. It's still got some of this, so it actually can still throw this back out and then that can be reborn back into it. So it's this continual process. And even in the explosion, you still produce hydrogen and helium because you can actually destroy heavy elements into smaller elements in addition to creating heavier elements from smaller elements. So it's this whole cycle, it's over and over again.
There's no shortage of high-grade thermonuclear fuel to make new stars. Okay, that's great.
We won't have to worry for a long time.
Okay. Another question from Charlie Sherney about the chemistry of the process. You didn't say anything about chemical bondings. Does that come into the picture at all, or is that you have to wait for the planets to form?
So you do have chemical bondings, but not in the wavelengths that we're observing. We're only seeing the emission properties coming from different elements, though. So you can see the different elements bond, or like different chemical bonding associated with it, but you have to go to a completely different wavelength to do this. But I didn't present any of that because I don't do the research on this. But yeah, absolutely you can do this. But and people do search for these lines, and that would indicate these different bondings or different elements. But for supernova remnants, mostly you're looking, or these ones, you're mostly looking for the emission lines from one particular atom. The resolution of our X-ray instruments are not good enough right now to be able to do this, but there is a next generation instrument that is coming that hopefully will be able to give us some more constraint on this in X-rays.
Okay, so I might just wrap up with two last questions. The first one is, can you trigger a supernova if two stars collide?
Yes, so I didn't touch on these actually. So you know how I said there was a core collapse? So when you have a very small star like our sun, right, they produce a core, carbon and oxygen core, and they kind of just die quietly. Well, that carbon and oxygen core forms something called a white dwarf. And a white dwarf can live for a long time. though, and it might be lucky enough to find a partner. It can either be another star, or it can actually find itself another white dwarf. And if they actually collide, if two white dwarfs collide, it produces something called a type 1a or thermonuclear explosion, which is a different type of explosion from a star, but from not massive stars, but from these low mass stars. And so we actually do detect these. There are a lot of them. And so when I showed kind of the images trying to understand the shapes of your objects, you'll notice that the more massive ones from these massive stars were more asymmetric and elliptical shape. The ones coming from these white dwarfs coming together, or these stars coming together and exploding, are actually more symmetric in shape. So you can actually even visually find them through this way. And they have different element production as well. So you can actually study this, but I didn't focus on that in that, but that's a great question.
And the final scientific question, there's one question from Joanne Dyer about our July lecture program, which I'll answer myself, but this one from Blake Bishop: are there any visible signs that a star will die soon that we should be keeping an eye on?
Yeah, so actually there is. Before a star dies, it doesn't go quietly from this. So what actually happens is that it actually kind of does little outbursts of eruptions or little explosions, kind of like, you know, if it's very hot weather, you start taking off your jacket. This is the same thing that a star does. It starts to get rid of material. And so what you can actually do is that you can actually look in optical wavelengths to see if stars are actually kind of bursting and disappearing, because this is essentially material that is being thrown out before it dies. But then what happens is that if you start throwing material out constantly, you actually hide yourself. So it looks like the star turned off, and then you have to keep monitoring it before it goes off from that. So a lot of the times we'll be looking at this, seeing a star kind of do this kind of fluxing that we observe. Or what will happen is that suddenly you'll be observing the sky and you'll see a little bump, and then suddenly a huge supernova that will go off. And that can be in a time scale of a few days. Wow. So it can be very quickly. And so you kind of can be caught at a surprise, which means that we have to suddenly move our telescopes and try to get observations to follow up. So it really depends on the star and what it's doing.
Wow. So the stars are giving up their secrets, and we're understanding them better and better every year. Yes. Well, Katie, thank you very much on behalf of the audience and the School of Physics for giving the final July lecture for 2020. I can see we didn't get around to all of the questions, but we've recorded them and we will come back and answer them, and you'll be able to find a video of the lecture posted online in due course. So and before I sign...
And thank you, David, for running the July lectures, these wonderful series. It's been amazing.
Well, thank you for that. So before I sign off, I should emphasize that the July lectures in physics will continue. I'm just signing off from managing them. They've been running since 1968, I only took over in 1990. But I'd like very much, on behalf of the School of Physics and the University of Melbourne, to welcome you all back for the 2021 July lecture program and all the ones thereafter. But next year, Susie Shi, who spoke to us a couple of weeks ago, will be running the program. So I wish Susie all the best in taking the July lectures forward into the future. So thanks again, Katie. Thanks again, audience. And that's it from me. Please stay safe and all the best. Good night.